Okay, so thank you very much for the kind invitation. So it's always a pleasure to be in Italy. So I will not reject this invitation, of course. So this, let's say, two first lecture of today, I will give mainly a brief introduction to generative model and give you a kind of tools. Okay. And from what I've heard, okay, you have the audience have different background, and we say that's. I will try, in fact, that everybody know, everyone here, in fact, are the same, are on the same floor, and I'll give you, okay, so I hope enough, in fact, material for you to understand, in fact, Giovanni's talks, and give you somehow the motivation and the main tools to generative models. Okay. So today's course, I changed a bit, in fact, the content of my first two lectures, okay, because of course, I was a bit too greedy, as usual, preparing my lectures. So in fact, I will give you first some introduction, basically on generative models, some motivation, and mainly, okay, I will try, in fact, to show you some fancy application of a generative model, but okay. A lot of people maybe use now ChatGPT, and okay, ChatGPT is a kind of generative model. Okay, so we have no doubt about the interest of such a model. Then, okay, I will switch to the most naive generative model, which are minimum distance estimation, okay, which was somehow the first generative model. And in fact, it will be just an excuse for me to present you metric and probability spaces, which are in fact at the core of generative model. Then I will give you one of the most simple generative models, which are based on the so-called normalizing flows. And particularly, will take some time about some implementation tree of this kind of generative model. And then, okay, I will switch on the last part, which is energy-based models, which are also very simple generative models, which was one of the first one. And give you, in fact, also, I don't know if I will have some time, but okay. At least Wednesday, I will give you, in fact, some relation between energy-based models and so-called score estimation, score generative model. All right. So it's not here, it's here. Now, okay, so let's talk about the general framework. Okay, so here, during all this talk, okay, I will take a state space X, okay, living in RP. So sometimes, in fact, P is equals to D because I'm not very consistent, but okay. So here, I take a subspace of RP, but in general, okay, it's just all the space. Okay. Don't bother, but it's just, okay, just to ease the notation. And now, okay, what's the goal, basic starting point of generative model is that, okay, you have some data xi, which are supposed to be IID. They are supposed to be IID observation from an unknown distribution, mu star, which, and here, okay, all this force I will denote by P of X, a set of probability measures on X. And now, based on this data, okay, I want to create new sample from mu star. So that's the basic, in fact, the goal of generative model. Okay, and the basic, let's say, recipe to create a generative model, in fact, can be listed as follows. So here, in fact, you consider a family of distribution indexed by theta. Yeah. And now, okay, of course, you suppose that you are able, in fact, to sample from mu theta for any theta. And now what you try to learn this parameter theta, which explains the data, which fits the data. And here, okay, I will somehow list two approaches, which I call the stochastic or statistical approach and the transformation approach. There are, of course, two relations between these two approaches, but somehow, okay, it's the two main recipes to create generative model in a nutshell. And okay, what in fact, what consists this approach? In fact, this approach, because here the main issue is that, okay, how you can define this family of probability distribution indicated by some parameter. So here, in fact, in the stochastic or statistical approach, okay, so here, what you suppose that you specify, in fact, for any theta, you specify the density of new theta with respect to a reference measure. In statistical stochastic approach, here, in fact, you do not somehow have access to the distribution in itself. Okay, you have distribution to a density. Okay, so it brings some computational challenge, as we'll see. But somehow, okay, it's quite easy to. We'll see. In fact, it can be easily to handle. Okay, and that's okay. The first approach. And I will give you, in fact, some example of how to specify the density and how to fit now the parameter theta to your observation. That's okay. And two examples I will give you today is like normalizing flow and energy-based flow. And okay, and another, in fact, another approaches, like which is now quite popular in machine learning is okay. Now what you specify, okay, now instead of specifying a family of distribution, you specify a family of transformation, T theta, parameterized by theta. So basically, in fact, theta will be neural networks. And now, okay, for mu theta, we define mu theta as a push-forward measure of some reference measure mu by T theta. So here, just give you the definition again. So what I call T theta sharp mu is equals to mu in some set A. It's just mu of the reciprocal image of T theta. And of course, mu, in fact, you suppose that you can sample from mu efficiently. Okay, if you can sample from mu efficiently and evaluate T theta, okay, sample from mu theta is very simple. Okay, so here, in fact, you know that T theta of Z equal theta if Z is distributed according to. So as we'll see, in fact, in the case of normalizing constant, or even more complex generative model. In this case, okay, you do not, in fact, you may not have, in fact, density, and you need, in fact, to consider, you need to design appropriate learning procedure. So typically, for example, you could think about GAN, okay, for this kind of approach. Okay. So now, in fact, I will try to address the following question. So now, okay, let's suppose that I have my family of distribution mu theta. Okay, I will give you some example in the mainly in the second part of this course. But now suppose that I have mu theta. Okay, how in fact I can fit the parameter theta with respect to the observation xi. So that's the first question which I will address in the first part of the course. Okay. So just some application of generative model. So first useless one, which is this one. I hope it works. Seems to work. So it just brings, in fact, cat picture. Okay, so you can see that it is a bit useless, but except if you are very fan of cats, but you can see that it works pretty well, except that for some of them, okay, they are quite strange cats. For example, I don't know if you see it there. This one is a bit, okay. I don't recognize really a cat, but even this one is a really big cat. But anyway, for some of the picture, in fact, it looks like really cats. Okay. So that's the first for the first application. So somehow it was the first. In fact, at the beginning of generative model, from what I remember, in fact, people was not even convinced about the application of generative model, because in fact, all the application was consisting in creating some useless image of MNIST or cats. Okay, but now people agree that in fact we have fancier application of generative model, which I give right now. So now I consider in fact what is called linear evidence problem, which is a very in fact general problem in signal processing, where in particular, okay, I work a lot on image processing, and okay, the most simple, the simplest problem is just that you have some blurred image and you want in fact to denoise image. And to this, okay, you just take a very simple linear model. So you assume that your observation Y is a linear transformation of your original image, okay, which is denoted by X here, plus some Gaussian noise. And now you want to recover X. So one simple option to do so, yeah, is in fact to minimize this function. Okay, so here you have two terms in this function. The first one considers that okay, you want that the image X in fact applied to from which you apply a, it looks like in fact the observation Y. So here it's enforced somehow that the reconstructed image should in fact lead to the same observation. And then in fact you penalize a bit the reconstruction because it is a ill-posed problem in general. And here you penalize the reconstruction by what I call P star here. And P star in some sense intuitively should in fact measure, quantifies how likely an image is. Okay. And here comes generative models is in fact here in P star we now in fact train generative models, okay, to construct what is called prior, which is exactly okay, this density P star. And in fact, you can see that from this kind of prior, you can reconstruct quite efficiently, in fact, blurred or noisy image. So that's not at all useless now. In fact, it brings really that generative model are really, in fact, at the core of statistics and machine learning nowadays. Okay,
But
so
that's not.
yes.
One is the real one.
No, the two in fact are two reconstruction, because okay, here I didn't want to enter the detail, but in fact here it's some sample of the posterior distribution, because here in fact I do not completely minimize this. It comes from one of my paper. Here the problem is not to minimize. We didn't try in fact to minimize this function, but to sample from the potential which is proportional to exponential means minus this. So it's let's say that we do you know a bit about Bayesian inference or not? So here in fact we don't, in this example we don't compute the map, we compute in fact some sample from the posterior distribution, because here you can correspond to the map here. And here the application.
Just a clarification question.
Sorry?
A clarification question. So the y in the first equation and the y in the second equation is the same.
Yes, y is the observation. Yes, it's this one.
Y is here.
Is this?
But the second y is an estimated y.
No,
The y
it's x that you try to estimate.
but it seems. Okay. Sorry, I didn't understand the point, but it seems to be g.
No, here in fact g is the noise. Here and you take a
Yeah,
statistical
but if
model.
you substitute over there, you are minimizing the noise. That's correct.
No, but here because here, yes, you try, but G is just a statistical model somehow.
Okay.
So here, if you know that just about statistics, so here, if you look at in fact this model, if G is some Gaussian random variables with unique variance, right? You recognize that in fact the likelihood of y given x, right? So here y given x, okay, it's just a Gaussian. So it's proportional to exponential minus 8x -1 as well. And so here, okay, now if you take in fact the log likelihood minus the log likelihood, you get exactly. And now, okay, you want to minimize the log likelihood, but since it is a ill-posed problem, okay, you need to penalize, in fact, the minimization with respect to x. Okay. Is it clearer or? All right. So here now, okay, so that's one of the examples. So, but now, in fact, in many applications of many today's application, in fact, you do not only sample from a target distribution U star, okay? But what you are interested in, you are interested in sampling from condition distribution. Okay. So here you want somehow to sample from a family of the distribution U star so that you have, in fact, some observation. And pretty much, in fact, to handle these cases, there are more or less simple or complex adaptation of, let's say, non-condition generative models. Okay. So I will not discuss this, okay, because it will bring us too far. But in fact, in let's say many applications today, we need in fact to consider condition generative models. And one example which I want to show you is this one. So here, I will try to give it on my laptop. Here, succeed. Yeah, we not. Okay, it does not work. Right? I know. Yes. Okay. So here, in fact, we can find this kind of model. In fact, it is based on diffusion model that I will discuss on Wednesday, and Giovanni will push a bit the discussion. In fact, you can find this kind of model very easily on the web. And here, in fact, I just, in fact, upload this model. In fact, in this model, okay, what you try to do, and in fact, it was how, in fact, I create the image for the website. In fact, I don't know why it's so small. It's a bit better now. In fact, in this type of model, what you're trying to do, so you do not really see here, but in fact, you try that your generative model takes as input a prompt, okay, the sentences, and in the model, in fact, I just upload. The model should in fact give you a picture corresponding to the sentence in the Monet style. Okay. So here, in fact, I just ask for a monument from Rome and give me exactly this. And another example is also on the website. Okay. And in fact, it's quite easy to upload such a model because now, okay, it's a diffusion model, very popular. And another, in fact, and you have a lot of, in fact, such generative model depending on the style that you want. So here it's some kind of a Monet style. Okay, it's a French painter. But here, if you want a more natural image, here one of the outputs. So that's in fact one application from another application of generative models, which in fact is quite popular nowadays. And now you have even OpenAI, which brings somehow very fancy solution. And now, okay, the last application which I want to show you is somehow the converse of the other objective. So here you have some image, and what you would like. You would like that the generative model gives you, in fact, the description of your image. So here, in fact, we develop some kind of architecture with one of my PhD students. Okay, and of course we do better than the other, but okay, I will not take this. Okay. So I hope that you are a bit motivated about generative models, and now we dig into the details. And I will start with somehow the easier way to proceed, which is minimum distance estimation. Okay. So here I will suppose first, as I said, that I have a family of distribution in theta. And now, okay, how can I simply somehow fit the base parameter theta to my observation? So somehow, okay, maybe for some of you it would be very easy, but as I said, okay, I've heard that okay, people have different background, and I will in fact give you the main ingredients to understand the further lectures. Okay. So here, in fact, what consists MGE, okay, for minimum distance estimation. So here now, if I have in fact my family of distribution in theta, minimum MDE, okay, which will go back to Wolfowitz. Okay. Now, in fact, more than 50 years ago. It just consists that to consider a divergence or metric on the space of probability measures, and try, in fact, to minimize the function which from theta gives, in fact, the divergence of theta with respect to mu star. And of course, mu star is again okay, by data distribution. So now, if you are able, in fact, to minimize this divergence, now you just set okay. Let's say that I have my divergence. You just set theta star belongs to the arc mean possible of the divergence of theta with respect to mu star. And you just okay get a new sample from mu star. You expect that a sample from theta star should be close to mu star. And now, okay, I will spend a bit of time to give you some example of such a metric and divergence. So we go on the board now. So I write with this.
Yeah, okay, okay. Do you need the whole board or do you manage to keep it there?
I will try to keep it there. Okay. So here, in fact, it's a metric. Can I just have some? So here, in fact, I will just focus on the space of probability measure on RT. And just okay for, I think everyone know here about the weak convergence. So here, some reminder. That if you said that okay, mu n converge weakly to mu. If for any function f in C 0b of RD, you have that mu of n of f converge to mu of f. Where not in fact mu of f is the integral of f. In fact, maybe you some of you know it, but okay, you can in fact define a distance, okay, such that the set of probability measure of RD, this distance in fact metrize this convergence. So here, what you know, that's there exists a distance and P of RD. Take that. You know that UN converge weakly to mu if and only if the distance between UN and mu goes to 0.
No, so I really meant if you can just
Okay.
yes.
Okay, I will try. Or maybe can I in fact? Yeah, it's maybe too small. Yeah. Can I not just take at least this part of the board, or it's,
Which part?
this one? Yes, because otherwise it's.
No, so you can use the other part. Just zoom out. But okay. Just use
Okay. So some example. Such a distance, so you have in fact the Lévy-Prokhorov distance. Which is in fact quite a complicated form for those of you who know it. In fact, I can give you the exact expression of this. You will see that it's not that simple. So here it's the inferior over all R positive, such that for any mu, for any F in RD, goes mu of F is smaller than mu of F plus the whole is center at 0 with values R plus. So you can show that, okay, this in fact is a metric, but again, it's not, in fact, you cannot in fact compute it efficiently. Okay, in fact, using it in fact for MD is not practical at all. You can forget about it. I know in fact one of the papers would try without much success, but they try. So another one, in fact, which in fact will be discussed, which may be used in fact for the analysis of generative model, by the way. Now, what is called in fact the Forte-Moyer metric. Which is in some sense the weaker metric than the Wasserstein metric that we'll see. So here it defines the Forte-Moyer distance, P of Fm between two distribution mu and mu as a supremum over all function F of mu minus mu F for F if it's from RD to R. And one. So again, in fact, this metric metrizes completely the weak convergence, but again, in fact, it is not. In fact, you don't have a simple way to compute easily this metric again. And now, okay, I will give you, in fact, some more practical distance and divergence that really you compute. But okay, we need to remind that in fact they are strictly stronger metrics than the Forte-Moyer distance or the Levé-Prokhorov one. So here, a distance which is now very popular in probability and now in fact in machine learning are Wasserstein distance. So here. So in fact, what is the Wasserstein distance? So here I first define the Wasserstein distance at order P. And to define the Wasserstein distance, I need to first define the notion of coupling or transference plane. So if I take mu and mu to distribution, I say that zeta, the coupling between mu and mu. If in fact the first marginal of theta is mu and the second is, so what does it mean? Here. It means that theta is the probability measure R2D. Theta dot times RD is equals to mu. And theta RD dot is equals to. And now, okay, I can define the Wasserstein distance of order P. The WP to the power P into mu and mu is equal to the infimum of the integral of x minus y P theta y for theta coupling between mu and. So I will give you, in fact, okay, I will detail a bit more about how to compute this in a few moments. Okay, but now I just want to give you a generalization of the Wasserstein distance further P, because here in the definition you can see that I use a norm. Okay, but somehow okay you can use whatever cost function you want or whatever positive function you would like. And now if I take O the distance on RD, I can define in fact the Wasserstein distance associated with rho between mu and mu. As again, in fact, the same definition as before, the infimum or the integral of x minus y is theta xy. Sorry, it's rho of xy. So here I just replace, in fact, the norm to the p by rho for x for theta between yes. And a particular example of Wasserstein distance which is very used, especially because from what I've come from, okay, because I analyze a lot MCMC algorithm, and in fact, the metric that we really like from the MCMC community is the total variation distance. So if I take O of xy as a trivial distance, so what is the trivial distance? It's just, in fact, the vector function that x different from y. So in this case, in fact, the Wasserstein distance, so here it's, let's say, ρ0. The Wasserstein distance associated with ρ0 between mu and nu is exactly the total variation distance, which can be also expressed as the sup, sorry, the sup between mu f and mu f for f compared to r on measurable. So here, in fact, in general, okay, many metrics, okay, and non-metrics can be expressed as a particular Wasserstein distance. So that's for the Wasserstein distance. So I promise you to give you some recipe how, in fact, to compute this Wasserstein metric. So in dimension 1, it's quite simple. So here I consider the case of the computation of W1. So here I will give you just a brief introduction about, in fact, some illustration of coupling. So on R, yes, you can easily, in fact, define coupling between two distributions. Also, so on what, in fact, maybe you should know this, but if X is a random variable system, you know that if I denote by F inverse X u, the quantile function associated with X, so the infimum over X R, such that F of X greater than U. You know that, in fact, F inverse X of U is distributing according to mu for any U uniform on 0, 1. So based, in fact, on this remark, okay, you can define easily, in fact, the coupling between mu and U as follows. So for any, if I take any couple U1, U2, couple of random variable, such that marginally U1 and U2 are uniform over 0, 1. Then I know that based on these simple results, the couple on a variable F inverse mu U1, F inverse U2 is a coupling between mu and nu if F inverse mu and F inverse nu correspond to the quantile associated with mu and nu. Again, F mu and inverse and F nu inverse correspond to the quantile function. In fact, what is somehow natural is that in fact, for the Wasserstein distance, if you take in fact U1 and U2, it corresponds to the optimal coupling for the Wasserstein distance of order 1. So here you have small. The point is not that easy, I would say. You need to think a bit to show it, but it's a nice exercise, by the way. So here, in fact, proposition as follows. The Wasserstein distance between mu and nu. Yeah, mu and nu are in P of R. It's exactly equals to the integral from 0 to 1 of the absolute value F inverse mu u minus F inverse mu u du. And so it gives, in fact, just a statement that, in fact, the coupling which achieves the infimum is the definition of the Wasserstein distance of order 1 on R. Is exactly, in fact, the coupling I gave you before, but for the on a variable u1 equals u2. So for R, somehow it's relatively simple to compute the Wasserstein distance. If you have access to the quantile function of u and the quantile function of u. And now, okay, if you want to compute the integral, okay, one simple option is just to use, in fact, the Monte Carlo procedure. Because we don't want to use some numerical integration. Yes. Well, here we rely solely on probability. So here you can just approximate W1 u yeah, as 1 over m, the sum of m inverse mu ui minus inverse ui. I equals 1 to m. Yeah, where are you right? AID uniforme de 0. Yeah. So that's for the one-dimensional case. And you could wonder, in fact, if you have some kind of extension for the d-dimensional case, for the multivariate setting. And fortunately, not, it's not that simple anymore. But in fact, you can use, okay, and it has been popular recently in machine learning and statistics, you can rely on some what is called a slicing strategy. Okay, so here, for the case of RD, you can use, in fact, what is called the slice Wasserstein distance. In what consists, in fact, this slice Wasserstein distance? It just consists in projecting. So here, in fact, it consists in taking a random vector on the unit sphere, project your random variable along this random vector, and take the Wasserstein distance associated with this projection and take the expectation. So formally, here you take mu and nu this time linearly. What you try to, so here just from a probability point of view, here let's take x and y in so let x mu and y. So here I define the slightest certain distance between mu and mu. So here I take the integral over the unit sphere of the certain distance of the image of the projection on V of mu with respect and the projection along V of mu sigma dV, where sigma is a uniform distribution in the sphere. So here you can show that okay, this defines somehow metric, okay. The convergence in this metric implies a weak convergence, and okay, you have somehow some equivalence with respect to the certain distance. And why, in fact, you can compute this metric this time? You can rely again on some Monte Carlo strategy. Because here, in fact, if I do not look at the integral, if I just, for a fixed V, if I look at in fact, the certain distance of this two distributions, so these two distributions are exactly, in fact, one-dimensional distribution. So since, in fact, they are one-dimensional distribution, I know, in fact, how to estimate the certain distance between these two distributions, these two one-dimensional distributions. And now, okay, I need just to take the average with respect to the uniform distribution of this. That's, in fact, all this, in fact, I can simulate it more precisely, okay? I can estimate this certain distance by just changing a bit my formula here. And so here, I can estimate the slightest certain distance of order 1 between mu and mu. So again, in fact, I will use the Carlo strategy. And here, okay, I in fact consider some a certain distance, what I denote W at 1 x vi x vi y. It's not at all in fact an interpretation, so we take it more precisely. So here it's proj vi proj vi where the vi are ID uniform on the sphere. So the vi here are ID uniform sphere. So I can just take them, in fact, as some normal on the variables divided by the norm. And now, for this quantity, which I denote W as 1 for mu I do, I can again, in fact, do a Monte Carlo algorithm, okay, to estimate this quantity as just 1 over M2, M2 da, let's say, for G equals 1 to M2 da of the quantile function associated with this distribution, okay, which I denote, let's call it mu I, and this mu I. And here it's 1 over m theta from G equals 1 to m theta of f inverse mu I minus f inverse mu I. G minus f mu I. So you use, in fact, the double Monte Carlo strategy. Compute, in fact, the integral over the unit sphere but also to compute all the one-dimensional assertion instance. So you can see, in fact, that's why, in fact, it has been popular in machine learning, because that's okay. You can compute, in fact, explicit distance, but there are pros and cons. I will not lie to you. Especially, in fact, okay, the large dimension does not work very well, and somehow you forget it's going to, it's not it's a precise metric in the application from what I can see. So that's for the standard assertion distance. And now, okay, let's try. Still, okay, could we still estimate the assertion distance? And yes, we almost can. Let's say. So here, in fact, so going back. WP on RT. In fact, we can relax a bit the estimation of WP of mu and mu. We can try to replace this problem by, let's say, the simple one from a computational point of view, which is as follows. So here you replace this estimation by the estimation of WP mu at n, where mu at n and mu at n are empirical version of mu n. What does it mean? It just means that, in fact, mu at n is equals to 1 over n, the sum of the Dirac mass at xi, where the xi at RD from mu, and mu at n, 1 over n, the sum of Dirac of yi, or yi this time are IID from mu. Why, in fact, in machine learning is not a problem, that in fact in machine learning or in statistics, you never, in fact, have access to mu and mu. In fact, you have only access to the empirical version of mu. Right. So somehow, in fact, the main issue, in fact, that you want to handle is not with this one, but rather this one. And you have, in fact, some relation. In fact, you can quantify the convergence of this quantity to this one. Okay, there are a lot of results about it. And so here, okay, let's focus on this connection. And here, in fact, I will this time, okay, now generalize a bit, in fact, my problem. Because, in fact, this time I can. So here, in fact, I will consider two distributions, u tilde n and u tilde n. I consider two discrete distributions. On Earth. So here, what I mean by two discrete distribution, I mean that u at n are equal to the sum of w I u Dirac I and u at n, u tilde n, sorry, is the sum of w mu I Dirac by I, and I take the same number of atoms for these two distributions. And here Wi mu and Wi nu are the simplex of dimension n. So here W1 nu belongs to the simplex. function n. So it just means that all these coefficients are positive, they sum to 1. So now, in fact, let's try to compute the Wasserfeld distance between mu at n and mu at n. Let's try, in fact, to see in the eyes the problem of computing this metric. Okay, let's continue. So in this case, okay, what I know, so if I take any coupling between u tilde n and u tilde n, I can now decompose, in fact, the integral of x minus y squared theta as 3 terms. The first one is the integral of x squared theta plus the integral of y squared theta plus 2 times the integral of the scalar product between x, y, and theta. And here, okay, if I thank you. If I'm going back to the problem of computing the Wasserfeld distance, I want, in fact, to minimize this quantity over all the coupling. But in fact, these problems based on this for computation. So here, in fact, this integral does not depend on theta, because in fact, it's just because theta is a coupling, it's an integral with respect to mu tilde n. So here, in fact, I can forget this term, my optimization problem. The same, in fact, holds for this term here. So I can forget this term. And all I need to focus on now to compute, in fact, this quantity is just on this term. Okay, so here I want to minimize this term, so I want to maximize this one. And now, since everything is discrete, okay, so here I will keep tilde n here, right there. So if I consider now the integral of x scalar product is y into theta, since everything is discrete, okay, I know that in fact the coupling without loss of generality, I can suppose that the coupling between mu tilde n and mu tilde n is also discrete and supporting the couple of variable xi, yj. So here, in fact, I can write it as, in fact, x transpose m y. Where x, in fact, is the vector x1, xn. Yeah. And y the same, so it's y, n. And m corresponds, in fact, to the mass, okay, of theta. So m equals to then so theta of so mij, sorry. So corresponds to mij factor. So it's theta I yj. So I lie a bit there because here, in fact, it should be a diagonal matrix, okay, with size n times d, with in fact with each blocks, in fact, are times this color. So pretty much, in fact, and what is important is that now, in fact, we want to maximize, okay, this quantity with respect, in fact, the variable, in fact, becomes now the matrix M. And you want, in fact, to maximize this quantity over M. And you have, of course, in fact, constraints on M because you want that theta is the coupling between mu at N and between mu tilde N and mu tilde N. So here, we want now, in fact, maximize. So here, in fact, minimize this quantity. Boils down to maximize X compose M, Y over M. Under the constraint that, in fact, the sum of M ij equals Wi U by sum over U. And symmetrically, in fact, if I sum M ij over I should obtain WG. So here, in fact, for finite, for atomic distribution on the RD, in fact, I obtain that computing the Wasserstein distance boils down to a linear programming problem. And in fact, some algorithm have been developed, okay, to solve this problem in efficiently, meaning that, okay, in fact,
Do you have also constraint of the positive?
yes. So you want that, of course, that's the MIJ are positive. Thank you. Okay, so here, in fact, is a linear program problem. With convex constraints, and so in fact there exists algorithm solve this to obtain, in fact, to obtain the matrix M which maximizes. So, but in fact, okay, what was quite unpleasant, at least for people in machine learning, is that in fact this algorithm have complexity n to the cube, and it is quite slow. Somehow, in fact, we do not. We want, in fact, to relax how the complexity, the complexity of solving this problem. Okay, so here, the complexity of such algorithm are in work n squared. And somehow you would like more trade-off in that case. You can, in fact, pay the price to be less accurate this in solving this problem, but in the same time have lower complexity. So here somehow you would like, in fact, to speed up the convergence of this algorithm at the price, okay, of being less precise. And to do so, in fact, you can consider a relaxing problem. In fact, so now to get more efficient algorithm. you may relax B. Okay, voilà, the fixes problem. But in fact, so here, in fact, the main issue is that you are just linear itself. Yeah, and since you are just convex, because you are just convex, the complexity is quite slow. And here, the main idea is to relax a bit this problem by, in fact, adding a strictly convex function to the subjective function. So here, you can relax, let's say, a relaxed problem, which is in fact to maximize some x transpose m, y, minus psi of m, where psi is strictly under the same constraints. And here, in fact, I introduced also a parameter epsilon. So epsilon, in fact, principal should be small, okay, because if epsilon is small, okay, in fact, it expects that this problem is close, solving this problem is close to solving this one. And for psi, which is equipoise. Okay. And in fact, if you take for psi what is called some kind of particular Kullback-Leibler divergence, which I will soon define, you get back, in fact, what is called a thing called distance. And in fact, Giovanni will talk a bit more about, in fact, this kind of distance in these lectures. Okay. Okay. So that ends somehow a guided tour to a metric, and in fact, the three last one which I talked about is now very used in machine learning. But in fact, what is not, they are still in fact quite demanding computationally. And in fact,
You want to share that screen?
yeah, yes, I will. Thank you.
You have to stop sharing from that problem.
So here now. Okay, so let's say that I will in fact write it on the board because let's say I will continue on the board. So. Okay. So here now, somehow, okay, it's still in fact computing metric. It may be difficult in general. And the idea, okay, is just to relax, okay, to consider other functions. E from E of RD square plus, which does not satisfy, in fact, the axiom of a distance, except, in fact, the most important one for machine learning people, let's say. So in fact, this distance, this type of function only in general satisfies that the divergence between mu and mu are equal to 0 if and only if mu is 3. But they are not in general metric. Either that do not satisfy the triangle inequality. So since in fact they do not satisfy symmetry axiom and the triangle inequalities, they imply in fact some kind of strange geometry of the space of quantity measure. And somehow their use should be met with care. But in fact they are very, as we'll see in fact on several examples, and they are at the base of, they are at the core of most of machine learning algorithm and in fact even in statistics. And in particular, okay, the one which is like the two ones which will be used a lot during our course are the following one. In fact, they have very important relation between both. The first one which I will discuss is the product level divergence. Which is simply defined as the product between mu and mu is equal to the integral of the log mu. And so here, in fact, you can see that it satisfies the only axiom that I impose. Why is that? Because from what I know, from what you know, that's so the product is divergence. Since in fact minus log is strictly convex, or if I take in fact the minus here, I know that this can be written as minus the integral of the log of d mu over d mu. And just applying the Jensen inequality, okay, I know that this is greater than 0. With equality, if only if d nu over d mu is mu most everywhere equals to 1. And so you obtain that mu equals to. Yep. So that's for the callback labeler, and as we'll see, in fact, we'll use in all the example I will give you. In fact, we will use in fact the callback labeler which fits the parameter theta. And last but not least, okay, I will give you the Fisher divergence, and we'll take a break. So here, divergence between mu and nu, which is E nu, the integral of the gradient log of nu over d nu square. And you will see that in fact the Fisher divergence in fact is at the basis of what we call the score estimation is score estimation algorithm.
What is that formula?
It's a gradient. You take the gradient of the log of the density. And of course, it's plus infinity if you don't have the density. So in the second part, now in fact I will fix the divergence. Yeah. So we keep the divergence first with the pullback labeler. And then, okay, I will give you how, in fact, to construct practically the familiar distribution with theta based on two principles. The first one is normalizing constant, normalizing flows, okay, which is a kind somehow you can think of as a particular neural network architecture, which in fact helps the optimization of the pullback. And the other one is the energy-based model. And I will end up just by a few observation of between the relation between generative model and what I call already score estimation. So see you maybe in 10 minutes. So let's continue. So after this, get it was I said to a matrix. So let's specify the familiar distribution with theta. So first, okay, so as I said, okay, if we have fixed the familiar distribution with theta and the divergence, okay, and just something minimizing either the divergence between mu theta and mu star, or the divergence between mu theta, or with respect to the empirical version of mu star. Okay, and once, in fact, if you can minimize this function as a function of theta, okay, and you denote theta star or minimizer of such a function. Sample, okay, to get a new sample from mu star. Okay, use just sample from mu theta star. So pretty simple recipe, but still, in fact, there is a lot of gaps to fill. This and first, like, so two choice. You have two choice to make. In fact, you have three questions to address. First, the choice of this familiar distribution, of course, the choice of the divergence, and the choice of the how to minimize, in fact, the function from theta gives the divergence of theta with respect to mu star. And so somehow, in fact, if you look at all generative models, they correspond to a different choice of either the distribution, the familiar distribution, or the choice of the divergence, or the choice of how to minimize this divergence. And okay, somehow you really, in fact, just try to address these three questions depending on the data that you want to handle and the objective at that. Okay, I will skip in fact this observation because I don't really have time, but just to be okay, just a few words about it. That's okay. What is a bit, let's say, depressing generative model is that somehow you can always find, so whatever the data distribution, you can always find a divergence such that, in fact, the best generative model attend for this divergence corresponds exactly to the empirical distribution. But in the same time, okay, if you want to design a generative models, you would like to create some diversity, whatever it means. Well, but you would like really to not get new. You want to get new observation, not observation from your training sets. But at the same time, okay, if you really rely on MDE, in general, you cannot do better than the empirical distribution. And in fact, if you see all the measure discrepancy to measure the efficiency of a generative model, you can see, in fact, and you can check even in practice, that if you take the empirical distribution, it's the best generative model. Okay, so somehow it's a cautionary tale about generative model is that okay, the current tool to measure the efficiency of generative model does not take into account the fact that you want to create diversity, human knowledge. Yeah. So, I will be very happy to be wrong. Okay.
Sorry.
Yes.
You are saying that if you take the empirical distribution, for example, that the divergence is 0.
No,
you cannot do better than that in what sense?
So here, in one sense, is what it's in a minimax sense, okay, from a statistical point of view. So what does it mean? It means that okay, I can always find a divergence. Okay, in fact, it's also true for the I think for the Wasserstein distance. If you take the Wasserstein distance, you can always find a distribution, a class of distribution, such that for any generative model, the divergence between the generative model created based on n observation and your data distribution is lower bounded by some constant n to the power minus alpha. But in the same time, okay, if you take the empirical distribution, we can show that the divergence between the empirical distribution and mu has exactly the same quadratic consequence. So you cannot do better up to some constants than the empirical distribution. So it's a very statistical viewpoint somehow. That's okay. You cannot create better generative models than the empirical distribution. That makes sense.
Then maybe a quick question. When you show the cats, of course the cats are not samples because you have some that have 5 eyes.
Yes.
So how do we in practice do you noise the empirical distribution or?
No, that's the main issue. You don't really to analyze. In fact, there is not, in fact, a proper
way of
discrepancy on how to really efficiently evaluate the quality of a generative model. And somehow, okay, that's why, in fact, in many papers, you just show plots or pictures and see, in fact, the quality of the pictures. But it's
so you count
yeah.
flags of okay.
Yeah. So it's really empirical. It's judgment. Okay. So now, in fact, to train a generative model, you can rely on the 0,1 statistical principle, which is the maximum likelihood estimation, as we'll see. And okay, to somehow give you this principle, I will assume as in statistics, I will take, in fact, that's why, in fact, I refer to as the first approach as a statistical approach. So here, suppose that's my family of distribution mu theta, and it's a density with respect to a reference measure, and let's take, yeah, why not the Lebesgue measure. So here, okay, I suppose that's mu theta for any data as a density with respect to the Lebesgue measure, which is denoted by p theta. For the moment, let's assume granted the design of this density p theta. And as I said, okay, I will give you like 2 ways to construct such a density. And okay, what's important at the end, as I said, that okay, you should be able okay to sample from p theta, because you want to generate new sample. Now okay, let's grant it the choice okay, of p theta, and now okay, let's go back to the divergence. And so here, okay, I take my favorite multi-angular divergence. If you're a statistician, okay, like it, and so so here now, if I take now the Kullback-Leibler data distribution mu star with respect to theta, I have this expression, which is exactly the expression I give you with a minus. But and as I said, okay, what is the main in fact difficulty here is that you do not have access in fact to mu star. In general, okay, you cannot even evaluate this integral set. And the way to proceed I give you is that okay, you do not have access to mu star, you do not even know the form of mu star in general, but you have access to sample from mu star. And what you would like in fact to replace mu star by the empirical counterpart. In fact, Michele told me in fact 5 minutes ago, but okay, if you replace mu star by the empirical counterpart, the Kullback-Leibler divergence is not even defined. Is that right? Right, but in fact you can fact, rewrites the problem of minimizing the Kullback-Leibler divergence as just a function of an integral of mu star. Also, so here, look at the Kullback-Leibler mu star with respect to mu theta. I just rewrite it as the integral t mu star log of d mu theta with respect to mu star. And now if I suppose, okay, I lose a bit of generality, but if I assume now that in fact mu star is equivalent to my reference measure lambda, okay, then okay, I can write in fact the Kullback-Leibler divergence as minus d mu star log of t theta d lambda. And here I have plus the integral of t star the log of each mu star over lambda. And now, in fact, from what I can see from this expression, in fact, minimizing the Kullback-Leibler divergence is equivalent, in fact, to minimizing this integral there, which is always defined, right? Even if this time mu star is discrete. And that's why, in fact, I would not consider at the end the problem of minimizing, in fact, the Kullback-Leibler divergence between empirical version of mu star and mu theta. I would consider, in fact, the problem of minimizing, in fact, this quantity where I replace mu star by some empirical counterpart, which, in fact, is now well defined because here just an integral with respect to mu star, and you do not have density of mu star or mu theta with respect to the other ones. So here, now okay, I show you that in fact minimizing this quantity equivalent to minimizing this function of theta. And since in fact I do not have access to mu star, okay, but just to sample, okay, I just in fact approximate this integral by somehow population counterparts. In fact, I approximate this integral based on some my observation xi as the empirical average of the log theta of xi, because just by my assumption, I suppose that mu theta for mu theta has a density with respect to lambda, which I just denote by pt. Yeah.
Lambda is always the base.
It's always the base. Okay, so here, take it very simple.
So in a sense, you start with Kullback-Leibler, but in the end, you just minimize empirical against the longer of the sense.
Exactly, exactly. So here, in fact, it's just, and here you recognize if you have taken one statistical course, it's just, in fact, the likelihood, like the empirical likelihood, and you take, in fact, you maximize the likelihood. That's it.
Is this also why you put mu theta as the second argument in the Kullback-Leibler and not the first? Because you would not be able to do the trick if you compute the Kullback-Leibler to mu theta and you start.
Yes, that's true. But I
Would you
guess
pull out something? No?
it really depends, I would say. No, because for the choice, from what I know, in fact, for the choice of the Kullback-Leibler, it just comes from the generic form of divergence. So the generic form of divergence, from what I remember, something like t mu, the integral of some function t mu over d mu.
Yeah.
Here, in fact, you have some
Okay.
That's all. But in fact, okay, for example, we can discuss it later, but in fact, for some application, you can also consider in fact the codebase ladder between mu theta and mu star.
And you can still work with empirical versions.
You do, but in fact, in this case, you have access to some density of mu star.
Okay.
It's okay. It's another story. Okay. Okay. So now, okay, I end up with trying to minimize, okay, this empirical, my empirical likelihood. Okay. And to do so, okay, I will just present you the standard goal in machine learning to optimize a function, which is stochastic gradient descent. Yeah, so here, I will define a sequence of parameters theta k, such that if I have at iteration k plus 1, given my current estimate theta k, and define theta k plus 1 at iteration k plus 1 as theta k plus gamma k plus 1, the sum over, in fact, xi in some batch, bk plus 1, of the gradients of theta of my likelihood in my observation xi taken at theta k. Okay. So here you recognize somehow, if you are familiar with you recognize the gradient descent. But here, in fact, instead of computing the gradients over all the sum here, because the main issue here that the number of observations is very large, and is very large. And just the trick is that you just subsample a batch in your observation. So here at each iteration, okay, you take now perform the gradient step. Okay. Here it will be in fact the gradient ascent, if you want to maximize. Okay. You take in fact a step size gamma k. It should be in fact quite small. A random batch pk plus 1 uniformly in 1n. And now, okay, you just take the gradient with respect to this batch. You perform one iteration of the gradient ascent. And in fact, okay, the convergence of this algorithm has been subject of plenty of paper, and okay, you can show that under certain conditions it converge or not. But you have positive and negative results. But okay, I will take for granted that okay, I will apply in fact stochastic gradient descent to optimize my likelihood.
So this is stochastic gradient descent. Stochastic means the sample sampling.
Yes, you sample the batch.
And how do you compute the gradient with respect to the batch?
I will come to it. In fact, and that's in fact the plan for the next part of the talk. So here, in fact, what you would like, and I will answer that more afterwards, that you would like, in fact, to design a family of density p theta, such that exactly the first p theta should be sampled. You should be able to sample from p theta for theta, and you should be also, as you said, be able to compute the gradient of the log. And to do so, yeah, a first option which I will present is based on what is called normalizing flow. So here, in fact, I will take this time a transformation approach. I will take, in fact, for mu theta the push forward of a known distribution mu0 by a family of distribution t theta. And I will try, in fact, now to design such a transformation t theta such that, okay, I have still a density, okay, which is not very hard, okay, if you have supposed that for n theta, t theta is a C1 diffeomorphism, you just will, as we'll see, we'll just use the change of variables and so it will have, in fact, the density p theta. But the main challenge is, in fact, to design the t theta in such a way that the gradient is easy to compute. And that's what is called, okay, the family of transformation for which it is possible which address this problem are called in fact normalizing flows. And I will in fact present you in fact a few options. Okay, so here let's say a bit of introduction. So what you would like in fact for your generative model, as I said, you would like in fact that first easy to sample and also easy to evaluate, and easy to train. In general, okay, you have a simple distribution that address these two objectives. But the main, as we doubt, when you look at in fact the distribution of your data, it's not at all that simple. And they can be very complex. But the idea, okay, is to try to transform, okay, but by successive, in fact, simple transformation. We will in fact try to compile simple transformation, which in fact transform successively by increasing the complexity of the distribution, the simple distribution into complex one. Okay, so I will be more precise in a few moments. But first, okay, so here I will try to design, okay, a family of transformation theta parameterized by theta, which are C1 diffeomorphism, and why in fact I want to consider C1 diffeomorphism, because I want to use maximum likelihood estimation, and so I need in fact that mu theta admits the density, and if I suppose that mu theta is the Cauchy measure of T theta by the Cauchy measure of mu0 by T theta, okay, somehow okay, you could think about C1 diffeomorphism. So here, if you consider C1 diffeomorphism, okay, then in fact P theta then like P theta x is equals to Q0 P theta inverse of x, the determinant was the Jacobian of theta inverse of x. I get a simple change of variable. And here, okay, I denote by Q0 the density of my starting distribution, my base distribution with respect to the vector. So here, in fact, just I said that if I consider for C one variable with a distribution of 0, I consider now for any theta x which is equal to theta z, it corresponds x as distribution with theta. And this distribution with theta I need for density p theta, which is exactly this density just by the change of variable. So now, okay, you have in fact an expression for the density. What you would like, somehow, you would like in fact a distribution which you can in fact sample from, meaning that in fact the evaluation of T theta should be simple enough, of course. And second, okay, you want in fact a family of transformation T theta in such a way that okay, the maximum likelihood estimation associated with P theta is simple also enough. And it has been thought, in fact, during the time that, in fact, it was somehow complicated problem. But in fact, using the right architecture and using our networks, you can solve these two issues. And so, in fact, the basic idea, as in fact it is also the case for neural network, is just to consider for the transformation a composition of simple transformation. Why that? Because in fact, if you consider now M transformation, we consider a family of M simple C1 before 1,000. So here, theta I theta I 1 M simple. Then, in fact, computing the inverse of this composition and also the determinant of the Jacobian is also relatively simple. And that's the basis of also the neural networks. Because in fact, if you look at DI's neural networks, they are just somehow composition of linear and activation functions. And here the principle is a bit the same. So now, okay, if you consider this family of simple transformation, you have in fact access relatively easily to the inverse, theta 1n x. It just corresponds in fact to reverse the order of the composition. Yes, theta inverse and 1 equals with theta inverse and x. So still, in fact, you can compute, if you can compute it, the inverse for all the transformation, you can compute the inverse of the composition. And for the Jacobian, it's almost the same. Okay, it's a bit more complicated. So here, the Jacobian of T1 and inverse. Because in fact, for evaluating the density of theta associated with the composition, I mean, in fact, as I wrote here, you have access to the inverse, but also to the determinant of the Jacobian of the inverse. And here, okay, I will cheat a bit because I think I will make a mistake. Some products. Relatively simple induction gives that it's a product from K equals 1 M or the Jacobian of theta inverse K applied to T inverse M to K plus 1 X. Where in fact theta inverse M to K plus 1 is just the composition of the inverse of T M up to K plus 1. And that's it. So okay, the main message here is okay. Now if you have, in fact, if you have access to the Jacobian and the inverse of the simple transformation, you can compute okay the inverse of the composition and the Jacobian of the relatively easy. And since in fact you can have access to the inverse and the Jacobian, okay, you can evaluate completely the density p theta associated with the composition. And just okay as proof of concept, that's okay. It's not a silly idea to in fact use this composition of simple transformation. You can look at in fact which distribution you can end up. So here in fact, so here it's based on one paper by Rezete and Mohamed, okay, which in fact introduce a kind of such a simple transformation. And here are the base distribution, which corresponds to my mu0 here, okay, and associated with the density Q0. So up you start from the Gaussian density, and down you start from the uniform distribution of the cube. And now, okay, you apply, okay, just one transformation to distribution up to 10 transformation. And this transformation they use, they are called in fact planar transformation, and they are designed somehow such a way that okay, you can compute relatively easily the inverse and the Jacobian. And you can see that by composing this simple distribution, you can start from pretty simple, easy to sample distribution and obtain a complex one. And now, okay, what you would like is, so all these distributions are parameterized by some parameter theta. What you would like in fact, as I said, fit your parameter theta to your data.
Can you say something more about this planar transformation?
I will give you in fact exactly the, of course, the expression of the transformation and the Jacobian everything. So, taking for granted for the moment, okay, all my story about the inverse, the Jacobian, etc. If you look at, in fact, the likelihood associated with this, with the family of transformation theta, okay, the likelihood can be written as follows. Okay, so here, based on my expression for p theta, if I take the log, since in fact I have a product here, I can in fact decompose my likelihood into two terms. So here, in fact, I have the first term that corresponds to this product here. Yeah. And here P should be Q0, sorry for my typo. And the second one, of course, corresponds to this. Okay, so that's now, okay, you would like to maximize this log likelihood based on the data xi. And for this, okay, you can just apply now the stochastic gradient descent or ascent to maximize this empirical likelihood. But the main issue is that okay, somehow okay, you can evaluate P, the inverse of theta, that's fine, and the determinant of the Jacobian of the inverse, but it can be very slow. So here, the main issue in computing the gradient of the likelihood I just gave you, in fact, is correspond to this term here, right? Because now, okay, computing the Jacobian of a function can be relatively complex, and even more the determinant. Because in fact, the Jacobian of theta, okay, let's say the complexity in general is p times p, where p is the dimension. And if you take the determinant of matrix, okay, computing the determinant of the matrix is as complexity p to the cube. Okay. So just one iteration for one term in your stochastic gradient descent costs you at least p squared for a general transformation. So somehow, okay, the idea is, as I said before, is to design now the family of transformation theta such a way that okay, it's easy to evaluate, easy to inverse, but also which admits for which the determinant of the Jacobian of the inverse is relatively cheap to compute. And the main idea is just, in fact, to consider somehow what is called triangular transformation, meaning that transformation for which the Jacobian of the inverse, but also of the transformation, are just triangular. Because if the Jacobian of the transformation is triangular, you just need to compute, in fact, the diagonal of the Jacobian, and the determinant corresponds just to the product of the diagonal, and that's it. Now the question, okay, is how, in fact, design efficiently and express in a rich enough family of such a transformation. Yes.
P here is the size, the subsum.
P, in fact,
Is the size of the initial.
so P this time is so here is P this time is a size xi.
But then if you do the stochastic trade,
Yeah, in fact, the determinant is a Jacobian with respect to this. Because here you apply the change of variable with respect to x and theta. Theta is a parameter, you fix a parameter. So thank you very much for your observation, because that may be too fast. But yes, so here P is the dimension of your observation. And now, okay, you take the Jacobian with respect to x. The theta, and so here the Jacobian is the size P times P. So you have P to the cube for the theta. Okay.
And these transformations always have to go from RP to RP. They cannot go to larger or smaller.
So in fact, it has been suggested to such other transformation, in fact, from RP to RM with M earlier or smaller has been proposed. And in fact, you can, instead of the change of variable, you can use co-area formula. But okay, the training, from what I've seen, it's a bit of pain. It's a bit of pain for training, but in fact, some paper, in fact, explore a bit this side.
Did people try to replace deterministic maps by transition kernels of Markov chains and then invert the?
Yes, yes, but it's not clear, in fact, which Markov chain you want to use. And even for the training, add some noise somehow. So for the variance of the stochastic gradient set, in fact, it can be not very stable. But somehow it has been shown that for especially in fact if you want to use the normal flow for doing variation in inference, it has been shown that it's in fact you have a richer in fact class of function. Okay. So yes, there are plenty of development about this. If you have questions, do not hesitate. Okay, so that's in fact the planar flows which I just mentioned before, okay, given by Mohamed and Rosende. So it consists in theta of z. It's just in fact the identity function plus u times h w transpose z plus v. So here h wb are some parameter. Okay. W is in RP, B is a real, the scalar, H is a real function, and U, okay, is a parameter of dimension P. So H somehow plays the role of an activation function. So here, okay, you can try to compute the determinant of the Jacobian of theta. So let's do it together. So first, okay, let's compute so the determinant with respect to C. Yeah, myself a mistake. I take the Jacobian of theta. Yeah. So here I just obtain what easily is in fact identity plus U W transpose H prime of W transpose C. So here, in fact, you would think that I lie to you, because it's not, in fact, a triangular transformation. But still, in fact, I will give you, in fact, triangular transformation the next slide. But here, still, in fact, the determinant of this Jacobian function is relatively easy. Why is that? Is anyone, in fact, know what is, in fact, the determinant of this matrix? So here, so it's somehow a formula which is, it's a Weinstein-Aronsach identity, which gives you, in fact, the determinants of Jacobian theta of V is equals to 1 plus H. So here you just take the transpose plus H prime W transpose Z. So here U transpose level. So here you obtain this. And just in fact it's a corollary or a consequence more exactly of the determinants on IP plus AB, where AB, okay, are matrix of dimension R, P times N and R N times P. It also equals to the determinants of IN plus for A R times N and B. R N times So it's a very linear algebra trick. That's quite based in fact on this numerical trick. You can compute easily in fact the determinant of the Jacobian. So here, okay, that's for the planar flows. Okay, for planar flows, computing the determinant of the Jacobian of T theta is relatively simple, and since in fact the Jacobians of the inverse is just one divided by the determinant of the Jacobians of T theta, you have access to the Jacobians relatively easily. You have access to the Jacobians of the inverse. But in fact, what is not that simple for planar flow, but somehow you can use numerical algorithm to compute it quite efficiently. You do not have access to an explicit expression for the inverse. And so in their papers, they just use, in fact, Newton algorithm to compute the inverse at each iteration. In fact, it is relatively efficient. But in fact, planar flows have been replaced by, in fact, other normalizing flows, as we see. And now, in fact, there are plenty of new transformation T theta, which in fact are much more efficient. And are some examples. So here, since then, in fact, I just stopped in 2019, but okay. There are still, in fact, some paper on this subject. But I will just focus on two simple cases, which is called NICE and real MVP. Okay, and so for NICE, I do not like to use this type. So here the main idea is really to construct triangular transformation and how to proceed. So here I consider, in fact, I partition 1P. So here, in fact, I take an integer R. What I said, okay, the R first component of my transformation T theta applied efficiency just corresponds to the identity. So here, okay, really the restriction of T theta on the R component is just the identity. And then for the P minus R last component, I said that okay, it's a translation of the P minus R components. Translate by a function parameterized by theta of the R first component. So here somehow what you and here now in fact M theta is typically the output of an RNA. Parameterized by theta. So why in fact satisfy all the desired data of normalizing flow? Because in fact it's relatively easy to compute the inverse, because the inverse is just theta inverse theta of x. The R first component of the inverse just corresponds to the R component of x. That's the definition. And so and for the R, the P minus R last component, it just corresponds to facts. Also, so here I consider so it could be then just x R plus 1. You just inverse in fact this map and you obtain just that it corresponds to x R plus 1 P. Here you replace, you do not have any more a plus, you have just a minus. Minus and theta. 1. So at the end of
What is R? Is it fixed or?
so I will come to it later, but because in fact the idea is just to compose such a transformation, and so in fact, yeah, and so here in fact you I fix in fact the partition to 1R, but in fact you can just take any subset in 1P, but the story is the same. To transformation, to permutation, in fact, it's so in fact in general you take in fact random permutation or sequence. Okay. So that's for the inverse. Okay, the inverse is relatively easy to compute. And now for the determinant of the Jacobian, it's what? Anyone can tell me the determinant of the Jacobian of the inverse is simply 1. Yes. Okay, so here you can see that it is relatively easy. It does pretty much the job. Okay. And okay, in the original paper, okay, what's in fact this final layer, because as I said, okay, you compose, that's nice, consists in composing such a transformation as in a neural network fashion, and just you end up with just a dilatation layer where in fact you just transform theta by control C, you just multiply each component by some parameter SI, you can try to optimize, okay, and again, okay, I will not give you here, but okay, the inverse is almost trivial, and the same for the Jacobians. The Jacobians just consist in the product of the SI or the product of the inverse. And you obtain, okay, this result, so it's very, very small, sorry for this, but when you look at, in fact, the result of the paper, it's still, in fact, quite blurry. And in fact, what people suggested is that the transformation here are not explicit enough. And one of the reasons that people have spotted is that precisely that the Jacobian is too easy, meaning that okay, the transformation is each of the transformation are volume preserving, meaning that okay, the determinant of the Jacobian is equals to 1. And the idea is that okay, can you somehow try to modify a bit this recipe such a way that okay, the inverse are easy to compute, but the Jacobian okay, does not preserve anymore the volume, and you can try to debate okay, the P minus R coefficient at the end. And that's what's
This map that you have written here, you applied several times, changing the
yes, the R and the theta. So here you have, so for each layer, okay, you have the difference of our network. First. But in general, okay, you do not try to use, you have, depend on the GPU you have. Okay. And in fact, it turns out that trying to get non-volume preserving transformation are relatively easy. Meaning that here, the main idea is to change just a bit this transformation. In fact, multiplying the component wise the P minus R components, the P minus R class components, by the vector, sorry, so here it's vector C R plus 1 P. So here you multiply component wise the P minus R component by a vector which is exponential alpha theta C1 R. So here is from what I come from, it's called the black lab multiplication, or in fact just the components multiplication. Alpha theta now is also a neural network, which takes as inputs the R first component of C and outputs a vector of dimension P minus 1. You apply the exponential map to each of the components, you obtain still, okay, a vector of dimension P minus R, which component-wise multiplied by so P minus R plus component of C. And again, it's correct because you inverse are relatively easy. Because, okay, the same as here, but try to multiply by exponential minus alpha theta of x1 R. You have maybe I'm going to suppose
sorry, and the theta you want to optimize over are all the collections of all the neural networks that you have used in every day.
yes. But yeah, in fact, it is not that. As you will see, in fact, I will give you, in fact, because at least for nice, the inverse is relatively easy. So in fact, to perform the gradient of the likelihood is very cheap. Because here you just need, in fact, to compute the gradient with respect to the parameter of neural network. Work by propagation. And as we'll see, in fact, it's the same for the J-project, for P and D. So here, for the inverse theta x 1 R is equals to x1 R. So R plus 1 P is equals to x exponential minus R is 1 R x R plus 1 P minus m theta x 1. So here taking in fact the gradients of theta of this function. Okay, so here you will, in the likelihood, you will have in fact P theta P, so Q0 P theta inverse of x. We need in fact to compute the gradient of this. Then computing the gradient with respect to theta of this, just in fact corresponds to Q0 to the gradients to the gradient of Q0 applied to theta It's yes, check yes. It's a Jacobian of theta inverse. Perfect theta radius of Q0 inverse. But each time, in fact, here it's a triangular matrix, and so here it's relatively cheap to compute. And in fact, when you do, in fact, if you use PyTorch, you can just implement this function. The gradients is done automatically. You can use AutoDiff for this. And now, okay, for the Jacobian, for the determinant of the Jacobian, it is also relatively easy. The determinant of the Jacobian of theta plus x is equals to this. Someone can tell me, in fact, what is the determinant of the Jacobian? Well, it shouldn't be that hard.
Science.
So it's a exponential minus the sum of alpha theta on R. So here it's from from R plus 1 to B. And that's it. So again, in fact, if you implement it, you just need, in fact, using PyTorch, you need, in fact, to implement this. Okay, there are, in fact, other tricks because you need to use what is called you need to rely on some variance reduction techniques. That's not exactly what you do in practice, but okay, for the determinants of the Jacobian, okay, you just need, in fact, to implement it as it is, and okay, you just ask for the gradient and that. Okay. And so here, okay, using N and VP, so it's paper of the business some example for the original paper. You obtain, okay, much clearer images compared to flags. And okay, you can also play a bit with the latent variables to have some kind of interpolation, and you can obtain such a fancy interpolation between images.
Can you say what are the images that you show?
How
you start?
So here, in fact, what you can, you want to explain what it is here. So the idea, okay, so you have learned a map, okay, which gives you from, let's say, Gaussian random variables, give you an image using normal. Here, in fact, you can try to sample 4 Gaussian. Based on this 4 Gaussian, you can use, in fact, this interpolation between the 4, using with playing with the cos and the sin. And now, okay, you make that varying, in fact, the P prime and the 5. Can interpolate between these 4 images. Okay, and so here at the corner, you have the 4 images. And here, between them, in fact, you have varying the phi and the 5 prime. And you apply, okay, of course, the transformation. All right. So I will skip, in fact, all this. Okay, there are, in fact, fancier architecture, okay, for normalizing flow, which I will not talk about. And okay, all is on my slides, and okay, it will be put online. If you are interested, if you have questions, you can send me an email. But now, okay, I would like to spend more time on energy-based model, which is a new, not new, but another kind of generative model, which was one of the first one. And so here, okay, so the idea will be exactly the same as normalizing flow, meaning that okay, I will try to define a family of density theta parameters like theta, which in fact I will try to learn the parameter theta which in my data by maximizing the empirical likelihood. And now to define in fact my family of density theta, it is okay, I will take somehow the simplest choice. Okay. I will specify my family of density p theta by specifying the family of potential function or energy function u theta. So here u theta is basically the output of neural network, but you could think in fact for entropy maximum entropy method, it's not a neural network, but you could think about different choice for the energy function, but okay. Machine learning, it's typically the output of neural net. And here, okay, I change D for P. Sorry again, I will consistent in my slides. Here, okay. Now, okay, I have, since in fact I have specified my family of potential. Okay, what does it mean? It just means that based on this family of function u theta, I define my family of density p theta of x as in fact the density which are proportional to exponential minus u theta of x. And this density, of course, is as before, density with respect to the Lebesgue function.
U theta is a neural network, or it is the difference of the neural network to the data, something like that?
It's a neural network.
Why? What is the intuition? Because you want the energy of the network to be as small as possible. It's like a sparsity.
No, you don't. You just try to so what you just want to define somehow a rich enough class density. So here, if you know that okay, the neural network somehow are a universal class, right? If you have rich enough neural network, you should have rich enough density.
But the point is that in the end, if you want to maximize this likelihood, it means that you're going to minimize the energy, no? Because the p theta is exponential.
No, with respect to the observation, you have the observation. So here, what you have, so here if you now take this this family of density, right, you obtain the empirical likelihood associated with an observation. The sum, as you said, of the energy, but applied to the observation.
Doesn't it look like some sort of sparsity enforcement?
No. It's just that you define a class of density. That's it.
So the class of u theta is not built using the data, it's just some black box class.
Black box. And here, okay, the main issue now is that in the likelihood, in the log likelihood, you obtain also the normalizing constant of theta. Yeah, so here, Romain knows that if I take the log of theta of x, of course, I obtain as the first term corresponds to minus the sum of theta xk. Now, in fact, I have n times the log of the normalizing constant. And here, in fact, in this type of model, the main issue is really, in fact, as we'll see, how to compute the gradient of this quantity there is very difficult. And in fact, that's why, in fact, energy-based linear was not very popular at some point. But there have been again some kind of interest recently as well. Yeah, so as I said, now if you want to use stochastic gradient descent to optimize this empirical likelihood, for the first term, it's relatively easy because it's a neural network. Okay, so here you just take the gradient of your neural network with respect to the gradient of our neural network with respect to the parameters, so it's just by propagation. And okay, the main issue is that how you compute the gradient of the log of the partition. And to do so, okay, you can rely on what I call the Fisher and Weiss identities. So apparently, in fact, there are plenty of names for this, but so it's so maybe in fact you have heard under a different name of this different expression. So here now, if I take theta, the theta by definition is just the integral of exponential minus u theta of x dx. So if I assume that okay, I can in fact exchange the integral of the gradients. I suppose that all the assumptions are satisfied that I can in fact exchange the gradients and the integral, and then I obtain that the gradient of theta, then if it is true, it's simply the integral of minus the gradient u theta x exponential minus u theta of x. Another result, okay, just by position, I obtain that the gradient of the log theta is the gradient of theta divided by the theta. Now I can recognize that in fact this is exactly, if I put in fact theta as a ratio here, I obtain that it is in fact exactly the integral minus the integral of the gradient of theta of x. Theta of x dx. So from what I obtain at the end is that in fact the gradient of the log of the normalizing constant can be expressed as minus the integral of the gradient of my potential energy times theta. So now, okay, but I will visit myself a few moments, but okay, the basic idea will just be in fact to replace the in the gradient descent, you just replace in fact the gradient of the log of the normalizing constant by some Monte Carlo estimator of the gradient. And so that's for the gradient, but okay, but people have also been suggested to use some kind of second order transformation because you can in fact also have a nice expression for the Hessian of the last partition. So here I'm looking at the Hessian of the log. Starting from the expression, my final expression there, I can just in fact express it as minus the integral of u theta of x, theta of x dx. So it corresponds in fact because I change the gradients and the integral. So here I take I exchange the gradient and integral, and so I need to take the gradient of the product, and it just corresponds to the gradient of this function plus the gradient times the gradient of the density. Therefore, okay, for the second term, I just obtain minus the integral of the gradients theta x, gradient with theta x constant. And that's so now, okay, let's try in fact looking at again the gradients of theta of x, the gradient of theta p theta of x. Do not forget that in fact in p theta you have in fact the ratio of two functions of theta. So here the gradient of theta is function minus theta of x divided by the theta. So here in fact the gradient of theta p theta of x is again in fact the sum of two terms. Here are the gradients with respect to theta p theta of x equals minus gradients of theta of x p theta of x, which corresponds to the gradients of the numerator. And now for the second one, right here for the second one is minus gradients of theta, gradients theta graded by theta square. Okay, and here okay the gradients here of theta. You obtain again exactly. It's and so here sorry it's also and I have to specify exponential minus theta. So here I have minus u theta of x theta of x plus p theta of x, the integral of gradient u theta theta of x. And so at the end, okay, you obtain, if you combine all the terms, that the Hessian of the log of z of theta corresponds to minus Hessian of u theta of x, p theta of x, plus in fact the covariance system of the gradient of u theta with respect to p theta, meaning that it's an integral of gradient bar theta of x, gradient u bar theta x, p theta of x, dx, where the gradient u bar of theta of x equals to gradient u theta of x minus the integral of gradient u theta x theta x. So that's for the Hessian. If you want, you have to use second information. And as I said, okay, people have also try to use, in fact, the fact that you can have access to the some Monte Carlo estimator for the Hessian. But okay, let's focus on the first order information. So the main idea is that now you should use, in fact, the Fisher identity. You obtain that, in fact, the gradient of the empirical likelihood corresponds as the gradient of the first head, which just corresponds to taking the gradient of the potential function with respect to the parameter theta, plus the integral of the gradient of u theta with respect to theta, the integral with respect to mu theta. So here, now the idea, the main problem here is that it is an integral, it is an intractable integral with respect to mu theta. And just the idea is, okay, at each iteration of my gradient descent, I will try to sample from mu theta. So here now we summarize based on this expression that you can try. And hope maybe in fact I put directly to pseudocode. Yeah, in fact, that iteration. Let's say that you have want to define theta k, imagine and as n. No? And let's suppose that okay, you have at iteration k. You are at a given estimate theta k. So here you want in fact to use the stochastic gradient descent, and so here you define theta k plus 1 as theta k minus gamma k plus 1 gradients L and at theta. And this time, in fact, the gradients L and theta is defined as follows. So here we can have minus sum over I some batch of gradient U theta I minus gradients U theta of yi, where the yi are ID sample from U theta. That will be in fact the ideal stochastic gradient descent. So here, in fact, you take a batch of your data, okay, corresponding in fact the stochastic gradient part of this part of the gradient of the likelihood, and now okay, you estimate like using the same number of samples in your batch, you estimate by 1,000 estimator this quantity again. At iteration at the parameter theta. So the main in fact you have still in fact a computational issue because in fact the main issue is energy-based models. That's why in fact they are not they have not been very popular at some point. Is that in fact in general sampling from U theta is very challenging. You cannot exactly compute. You cannot exactly sample from U theta. You need in fact to rely on FCMC. And here, in fact, in the training of energy-based model, you need to specify for any theta an MCMC algorithm which corresponds to a Markov kernel P theta, for which in fact P theta is invariant for P theta. Okay. So I will not specify because you have a huge choice for the MCMC algorithm, but the one which I work on a lot is the Inaldi-Langevin algorithm, which is pretty simple in the case of energy-based model. Okay. So here, in fact, it just consists in applying and so considering for given theta. Okay. Now you do not take the gradients of the potential energy with respect to theta. You take in fact the gradients of the potential energy with respect to the input x. And based on these new gradients, okay, you can compute in fact for any theta, okay, you can compute this Markov chain, okay, and it gives you okay, you take let's say relatively modest number of iterations, okay, and at the end you obtain approximately a sample from theta, okay. And that's in fact what you can change here. Okay. So here, instead of considering ID sample from U theta k directly, you just in fact you replace for the yi. You take in fact I sample from some output of a large algorithm after a certain number of iterations, and you plug in it in the expression of the gradient of the large. And so at the end, okay, you obtain this beautiful algorithm where, in fact, it's exactly what I wrote on the board on the right here. Just, in fact, I just add a loop here, which consists in performing, in fact, the Langevin algorithm to exactly try to estimate, to have, in fact, approximate sample from new data, and to get, in fact, to obtain, to try to get an estimation of the integral of the gradient of Utica with respect to the Utica or theta in my current estimate. So that's it for today. Okay. I think I've done enough. So for the next course, I will give you, in fact, relation between the energy-based model and score matching and the minimization of the Fisher divergence. Okay, because as we'll see, in fact, score matching estimation is at the core of diffusion model. And then I will give you, in fact, a very gentle introduction to diffusion model without any technical tools, except that, in fact, transition density. That's all you need, in fact, to understand diffusion model. And it's based on the paper which has been published in École. And then, in fact, Giovanni will take the lead to introduce, in fact, a more fancy way diffusion model based on reciprocal process and give some analysis of this generative model. Thank you very much.